Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, do we have a problem? Do we use too much energy? Should we conserve energy? Can we conserve energy? Today we're going to talk about a weird idea called conservation of energy. And it doesn't mean what you might think it means. It doesn't mean that I'm trying to save energy at my house because I use too much electricity when it's hot here in Houston. It's something different. This is what conservation of energy means scientifically. This. Energy can't be created or destroyed. It can only be changed. So when you put gasoline in your car, which is chemical potential energy, and then you turn your car on, it converts that energy into mechanical energy and your car moves down the road. But you know what? Your car's not very efficient. Car engines are like 10, 12% efficient. Most of the energy, you know what it does? It heats up your car. You ever touched your engine? Don't do it. After you've been running it for a long time, most of the energy gets converted to heat. But the reality is the amount of energy that goes in has to equal the amount of energy that goes out. You're just changing the form of the energy. So that's conservation in a big picture, but it saves us a lot of problems. So let's particularly talk about mechanical energy, the energy of motion. We can say that the mechanical energy is equal to the kinetic energy plus the potential energy. So that's a mathematical equation, right? And if we have this, it simplifies so much of our math and stuff like this. But it's first of all true. There's also sort of thermal energy. That's actually sort of the thing that causes problems. There's also this sort of thing. That's the one that where the heat. So let's see if we can do a problem. It's kind of a complex one, I think, but it's kind of a cool one. It's the bottom of the ninth inning. A player hits a baseball. Over the outfield fence, the ball leaves the bat with a speed of 36 meters per second. The bleachers, a fan catches it. What do we know about this ball? So let's see if we got a picture, right? So I got a guy, baseball guy, right? Hitting the baseball. And he shoots it here, boom. And what do we know about this? It leaves the bat, by the way, the ball is 1.15 kilograms. That's the ball. So we know its mass. It's important. And he catches this 7.2 meters above where he hit it. All right? That's a 2. And the original speed is 36 meters per second. So he hit the ball. He really hit it hard. What's the kinetic energy of the ball just before it got caught by the fan? Here's the fan guy, right? He caught the ball, right? So we're going to use the equation, right? Kinetic energy. Kinetics 1/2 mv squared, so 1/2 times 0.15, 36 squares. This comes out to 97 joules. So this is the amount of energy, but right before it was caught. What is its speed just before it's caught? But that's the kinetic energy, right? All right. So the kinetic energy was we got, but we got to find the potential energy. So the potential energy, let's find this. This is equal to mgh. So this is equal to 0.15 times 9.8 times 7.2. And when we multiply that all out, we get 11 joules. Now, if these have to be this plus this, and actually they're opposites and negatives, I should have made a note. It's like they have to add up to 0. So the PE has to equal KE. If you would, this is 0. And the potential energy is positive, and the kinetic energy is negative. So we can set 11 joules, all right? So we get 11 joules, and actually, as it turns out, actually it will be negative 11 joules because one's positive, one's negative. So I've got the kinetic energy, I have 97 minus 11 equals the mechanical energy that is now converted into its velocity. So 97 minus 11 is 80 odd something, 86. So I can say 86 joules, and that equals 1/2 mv squared. We plug this in, you know, this is equal to 0.5 times 0.15, that's the mass of the ball, times v squared. And this is 86. We do simple math, we got to play a square root game, and we get a velocity, and this is going to make sense, of 34 meters per second. Meters per second. So does that make sense? It was going 36, and now it's going 34 because it didn't come all the way back. When we did like kinematics equations, we would have said, oh, that's pretty easy. We could figure this out, but it should be about this. It's the same if it goes back to level, but it didn't go to level. It went to 7.2 meters above. An interesting thought question. We've got a slide, got a kid at a water park or something like that. We're on a frictionless slide, and the distance here is, they start with a 0 velocity and a v final, all right? And this has a particular height of h. And then we have another slide that goes like this. Got the kid up here, but it's at the same exact height. And we want to find final. Which one will have the faster person? So as the ball rolls down, or as the person does the slide on a frictionless slide, which one will have a faster VF? Think about it, think about it. Potential energy is equal to mgh. Since the h is the h is the h, they're going to have the same final speed. Now they're going to have a faster acceleration here, but when it's all said and done, they're going to end up at the exact same speed. Again, assuming frictionless, they're going to have the same exact speed at the end of the slide. So kind of an interesting thought experiment. And the last problem in this series is we want to talk about a snowboarder. So let's two cases, right? So we got snowboarder number one. In case number one, he starts at a speed of 4 meters per second. He's going to go up a hill height, so he's already moving fast from probably running down the hill. And he goes up to here, and he gets to the top of this hill, and he gets to a final velocity of 0. Right? Second case, he's moving at 5 meters per second, and when he gets to the top of the hill, he's still going to have some speed. So the question is, what is his speed, since this guy was going at 0? Does that make sense? And so we know a couple of things about this guy. He has a mass of 75 kilograms. It's the same dude, right? So what we can do is we can find his kinetic energy, right? His kinetic energy right at this particular moment, which is going to then, he's going to lose it all when he gets up here to potential energy. So we can just say 1/2 mv squared. So let's say in case number one, 1/2 mv squared. And then we just plug in the numbers, and what we get is we get 600 joules, right? M 75, 4 squared. And then for case 2, now watch this one. What's his kinetic energy, right? You're going to say 1/2 mv squared. But instead of putting in 4, you're going to put 5, and then you get 940 joules. So what's going, even though we don't know this height, what we can do, and it's not important, we know that he picked up 340 extra joules. That's what he's got left over when he gets to the top. And then we can set that equal to 1/2 mv squared. All right, let's do this more specifically. Equals, 1/2 times 75 times v squared. We do simple math. We now solve for this v, and we get his new final velocity to be 3 meters per second. Because, right, we were able to subtract, we're assuming energy is conserved, and that's how we can solve these problems. Houston, we don't got a problem, because you are awesome. We'll see you in class.